We need to introduce manifolds with boundary because some of the applications of the techniques we are going to see, as for instance the degree of differentiable maps between manifolds of the same dimension, require to work with manifolds with boundary. So let us introduce the definition. We say that H is a half space of Rn, or n half space, if it's of the form, it's a set of points such that lambda of x is greater or equal than 0, where lambda is a linear map from Rn to R. Okay? If lambda is identically 0, then H is just Rn, and in such a case we defined the boundary of H as the empty set. The other possible case is that lambda is not identically 0. In such a case, the kernel of lambda has dimension n-1, and we say that H is a proper half space, and we define its boundary just as the kernel of this map. What do we need to consider when we work with manifolds with boundary? In a manifold without boundary, the target space of a local chart is an open subset of some Euclidean space Rn. It's just that simple. When we consider a manifold with boundary, the target space of a local chart is an open subset, but now of a half space of Rn. Okay, we are allowing not just open subsets of Rn, but also open subsets of half spaces. And since Rn is a half space, we already saw that, we just have to consider as linear map the map that is identically 0, a manifold is also going to be a manifold with boundary. It's going to be a manifold with an empty boundary. Okay? You probably already studied manifolds with boundary because they appear in courses of differential geometry. For instance, when it is studied Stokes theorem. In the Stokes, the formula of the Stokes theory is that the integral of a differential form at a boundary of some manifold with boundary, it's going to be the integral of the differential of such a form on M. And so in order to make sense of this formula, it is necessary to introduce manifolds with boundary and then the boundary of a manifold, okay? And this Stokes theorem has several versions. For instance, in courses of calculus, you can find the green theorem, the divergence theorem, but it has even applications, for instance, in complex variables. The Cauchy integral formula is just a version of Stokes theorem, okay? So let's be a little bit more precise with the definition of a manifold with boundary, okay? We say that a topological space X is a CR manifold of dimension K, now a manifold with boundary, if there exists an open cover UI of X and a family of homeomorphisms whose domains of definition are indeed the sets of the open cover, such that BI is now an open subset of a K half space for every I. Okay, that's just the analog of the first part of the definition of a manifold, in which we are just replacing our K with a K half space. It's that simple. And in the second part, when we consider the change of coordinates, we require that these change of coordinates are indeed CR diffeomorphisms between open subsets of K half spaces. Of course, whenever ui intersection uj is a non-empty set. Let's say a word about that. When we consider the coordinate change, okay, this is a bijection between these two sets, right? But these sets are not open subsets of Rk. So what does it mean that this map is a CR diffeomorphism? So we're going to say that it's a CR diffeomorphism if it can be extended to a CR diffeomorphism. If there exists a map, a CR map, a CR diffeomorphism, okay, such that the domain of our coordinate change is contained in W1 and the restriction of F to that domain is indeed our coordinate change. And so it's going to be that. It's going to be these coordinate changes are diffeomorphisms if they are restrictions of diffeomorphisms. Okay? So we don't have any issue when dealing with points in the boundary of our domain. Having said that, it's not clear so far why we can actually distinguish between interior points and boundary points. That's very intuitive. So let's see what we can say. Consider a local chart phi such that B is an open subset of a half space H. And U, of course, is the domain of our local chart. We want to define the intersection of U and the boundary of M. And we just say that it's going to be the preimage of the boundary of the half space. The issue here is that the definition of a boundary point does not depend on local coordinates. So imagine for a minute that we have a point X that belongs to the domain of two local charts. Okay? And suppose that for one of them it's a boundary point and for the other one is not. Let's say that that's not possible. And so the definition of boundary point is not going to depend on the choice of local charts. For instance, suppose it's a boundary point for the first one. That means that the image by the first local chart of our point X belongs to the boundary of the half space that we use to model that local chart. Whereas in the second case, the image does not belong to the boundary of that half space, the corresponding half space for the second chart. Okay? What happens here is that in the second case, B2 is actually a neighborhood of the point phi2 of X. When we have a half space, okay, and we have interior points, the half space is a neighborhood of the interior points. It's not a neighborhood of the non-interior points, of the points in the boundary, right? So we have this situation in which B2 is a neighborhood of the image of X by phi2. Now, what we do have is that this map over here, which is the coordinate change between phi 2 and phi 1, is a CR diffeomorphism. And in particular, is a diffeomorphism defined in a neighborhood of the point phi 2 of x. So you can use, in particular, for instance, the inverse function theorem, which is going to imply that the image of this set over here, okay, it's going to be necessarily an open set, and it's going to be a neighborhood of the point phi 1 of x. Okay, but this implies necessarily that the image of u1 is a neighborhood of phi 1 of x, and in particular, the point phi 1 of x does not belong to the boundary of h1, okay? Because if the half space is a neighborhood of the point, it's because it's interior. So we get that phi 1 of x does not belong to the boundary of h1. And we get a contradiction. So the definition of a boundary point depends on the choice of local charts. So we can actually, in order to see if a point is a boundary point, we can choose a local chart. We see if it's a boundary point for that local chart. And if it is, it's a boundary point of M. It's that simple. It's a property that we can choose in any local chart whose domain contains a point X. Okay, so we know now that for a manifold with boundary M, we can define the boundary of the manifold, okay? That we are going to denote like this, boundary of M. If the boundary of M is the empty set, we say that M is a manifold without boundary. Let's remind ourselves again that a manifold without boundary is also a manifold with boundary. It's something a little bit weird, but yeah, we are making that convention. And if the boundary of M is non-empty, we say that M is a delta manifold. Okay, so a delta manifold is a manifold with a non-empty boundary. Right. The atlas of a delta manifold induces an atlas of the boundary of M. And indeed, the boundary of M is a manifold without boundary of dimension equal to the dimension of M minus 1. Okay, let's see how we can actually understand this. Suppose that we have a local chart, okay, and the point X belongs to the boundary of M intersection with UI. What happens is that we also have a half space such that indeed the intersection of UI with the boundary of M is just the preimage by phi sub I of the boundary of the half space, right? The half space has a boundary such that we are considering that we are working in dimension small m, this is a subspace of Rm of dimension equal to m minus 1, right? So in particular, there exists that T sub I, a linear isomorphism from the boundary of the subspace Hi to Rm minus 1. And now it's not that difficult indeed to build the local charts for the boundary of M, okay? Because, okay, so we have phi sub I, we have that U sub I intersection the boundary of M is the preimage of the boundary of a half space H sub I, okay, and we have actually linear isomorphism from the boundary of H sub I to Rm minus 1. So what we need is building now a local chart, which is of course going to be a local chart for the boundary of M. We are trying to see that the boundary of M is indeed a manifold. It's going to be a manifold without boundary. So we have to build the local charts for such manifold. So the domain is obviously going to be contained in U sub I. So it's going to be U sub I intersection with the boundary of M, right? And the target space is going to be the image by T sub I of the image of by phi sub I of UI intersection the boundary of M, right? And what we do is we send a point to Ti applied to phi I applied to C, right? That's going to work very, very well because indeed the points that are in the boundary are the points that are sent to the boundary of Hi, and then we can apply Ti. And this set over here is an open subset of Rm minus 1. Okay? Now, if we consider the corresponding change of coordinates between these induced maps by phi sub I and phi sub j, what we're going to have is that we are just considering the composition of these maps. And this is going to be like this. So essentially here we have a map that is going to be a CR diffeomorphism, and in both extremes we have linear isomorphisms. So the composition is also going to be a CR diffeomorphism. That's easy to check out. And so in this way we get a trivialization atlas for the boundary of M. Let's point out that the boundary of M is a manifold without boundary, okay? It's the boundary of the boundary is indeed empty. Now let's define submanifolds with boundary. So we say that X, big S, is a CR submanifold, maybe with boundary of Rn of dimension K, if for every point small x of big X there exists a CR diffeomorphism phi between open subsets of Rn such that small x belongs to U and the intersection of U and big X is just the preimage by phi of the intersection of H and B for some k half space H. Okay, that's the definition. Let's see an example. Consider the product of the closed interval 0, 1 with a singleton consisting of 0 twice. Okay, and this is going to be a submanifold with boundary of R3. Right? It is very easy to check out at points of the form x0, 0 in the neighborhood of those points if x is greater than 0 and smaller than 1. So the points that are a little bit trickier, not much, but a little bit trickier are the points 0, 0, 0, in other words, the origin, and 1, 0, 0. Let's consider the first one. So we are going to consider U as being the set of points x, y, z in R3 such that x is smaller than 1. That's an open subset of R3. And we're going to define B also equal to U. And indeed, we are going to define phi as the identity map of U or B, okay? And in this case now, the intersection of U and X is the product of the interval 0, 1. It is closed at 0 and open at 1 with the set consisting of 0 twice, right? What would be H in this case? H is just okay, let's see if I can write it here. H is the set of points of the form x1, 0, 0, where x1 is greater or equal than 0. Okay? And this is indeed a one half space because when we fix the last two coordinates equal to 0, we're working in a line, and this equation actually defines a half space of the line. So a one-dimensional half space or a one half space, okay? And what we get in this case is that this is the intersection of H and U. And so in this way, we show that a neighborhood of the point 0, 0, 0 is indeed, it satisfies the definition of some manifold. And it's very easy to check out that this is a submanifold with boundary, in which the boundary consists of 2 points, the point 0, 0, 0 and the point 1, 0, 0. Okay? What we just gave is the definition, okay, of a CR submanifold with boundary of Rn. But sure, we want to define submanifolds with boundary of any manifold. So in the general case, we just translate the setting to Euclidean space. We say that X is a CR submanifold if for every point in X, if for every small x in big X, there exists a CR local chart that contains a small x in its domain of definition, and such that the image of the intersection of big X and U is a CR submanifold with boundary of R small m, where small m is the dimension of big M. It's the narrow definition, right? The issue here is that, for instance, in this way, we could consider, for instance, a half space. A half space is a manifold with boundary, and this is the boundary is just the boundary of the half space. But for instance, something like this, it is a manifold with boundary. If you consider this set over here, it's something that it is topologically a closed disk, okay? But it is a manifold whose boundary is indeed this curve. And in this way, we have two manifolds with boundary, H and N. And what you can see is that the intersections, the intersection of the boundaries is not very nice, because it's this sequence of points. But it is not very difficult to change a little bit N in such a way, that the intersection is indeed a countercept. So we're in a situation in which our definition of submanifold, of a manifold possibly with boundary, does not guarantee at all that the intersection of our submanifold with the boundary of the ambient space is indeed a submanifold of the boundary. Indeed, in general, it doesn't happen. So we have that intersections of our submanifolds with the boundary of the tangent space, those intersections can be very bad. Okay, it's what it is written there. A priori, the boundary of X of the submanifold does not intersect the boundary of the ambient space in a submanifold. Okay, something that we can do is providing a new definition of submanifold, which is going to be a submanifold plus something else, so that these intersections are actually nice. In this lecture, we introduce the concept of manifold with boundary. Indeed, if P is a manifold with boundary of dimension n, then the boundary of P is a manifold without boundary of dimension n-1. We also introduce submanifolds of manifolds with boundary. And we saw that in general, these submanifolds do not have a good position with respect to the boundary of the adjacent space. More precisely, in general, the submanifolds are not transverse to the boundary of the ambient space. Such a property will be required in applications, and indeed it defines the so-called neat submanifolds that we will discuss in our next lecture. Thank you for your attention.